start science today, and we'll have another set of lectures, Science 1 through 12. And the reason for grouping these lectures into a set is quite complex. It allows us to do very complex transformations of the material which a normal presentation would not have. If you teach by subject, subjects are tables of contents that arbitrarily slash through a considerate body of information. You can teach some things this way. It's called instruction. But you cannot educate this way. And so education has failed in every attempt to be delivered in this time-honored traditional mode of teaching by subject. In the 20th century, we discovered by the 1920s that the traditional subject separation of chemistry and physics no longer held. That classically, one taught chemistry and not physics, or physics and not chemistry, not because of understanding the subjects, but through an ignorance in the basic information underlay, which both chemistry and physics depend upon. We simply didn't know. And when we found out the structure of the atom, the structures of molecular materia, the difference between chemistry and physics as subjects disappeared. The fact that chemistry is still taught as a subject and physics as a distinct second subject everywhere on the planet is a sign of immaturity and of a failure of that civilization. And part of the difficulty that we have in 2001 is because that civilization failed more than 80 years ago already. It did not transform in the most important process that it has, that of education. So our education is rather new in terms of delivery, but has antecedents going back at least 3 or 4 generations in a concerted way. And as I hope to disclose in a couple of years in a very large, massive work, its antecedents go back, in fact, to Paleolithic origins, before civilizations even arose. So this is Science 1, and Science 2 will follow, but Science 2 doesn't follow just as another node on a line of instruction. Science 1, like a computer diagram, will morph into Science 2, and that will morph into Science 3, so that the experience that we have of following Science 1, 2, 3, and 4 is not a cardinal counting sequence, but is rather a transform by phases. And early in the 20th century, taking his cue from some artistic geniuses in the 19th century, namely Monet and Cézanne, Matisse in the 1920s began to photograph his paintings as he would develop them, so that one of the classic Matisses of that time period, called Pink Nude, had more than 20 phases which Matisse photographed, and one can find the records even in some rare books on Matisse. You can see how the painting changed. All of these changes were not emendations to a structure, but were structural morphs, so that the painting that we have now, Pink Nude, is an accumulated complexity. An accumulated complexity. This was done by Matisse consciously, developed out of Monet, who used to go to a site and used to make a series of quick paintings, quick sketches of the same thing, and repaint them or resketch almost every hour to catch this object in its dimensional morphing. The most famous example for Monet was his haystacks. And you can find dozens of Monet haystacks. They're the same haystack, but they are done not only in different times of days, different seasons, different color palettes. All of this was to show that our relationality consciously to an object changes the way in which it presents itself in reality. That it's not just a question of the observer interfering with the time and space of something, but that the observer adds a dimension, and that dimension, to use an old-fashioned term, factors into how it is in time and space. Now, this is extremely important when it comes to understanding science. We've chosen two examples, a man and a woman, from 20th century science, who were exemplary in understanding what Monet had set out and what Matisse had developed from that, with the addition of the fact that Matisse also used Cézanne in addition to Monet, and that Cézanne was distinct from Monet. Monet was an impressionist. He painted using color to give the impressions of form, whereas Cézanne was interested in structure, in the structural way in which form then made a different matrix that distributed color according to the form, and out of Cézanne came finally Cubism. Out of Cézanne came Picasso, the arch rival of Matisse. But when one looks at Cézanne's method of composition by structural faceting of vision so that color is distributed against this faceted vision in a way which would be natural, Matisse factored in the Monet thing that the distribution will change over time, so that Matisse's colors are filled with subtle Monet nuances, though they are in a Cézanne structural influenced vision. Something that, despite his genius, Picasso never understood. So that a Matisse, like a Matisse that one would look at, let's say, a famous painting of his from 1939, just called Music. Two women seated in a Matisse-type room, one of them playing like a guitar, a mandolin, and the other obviously accompanying her, and there's an open sheet of music, and there are some philodendrons in the background, and there are two wonderful women at home in a gorgeous array of Matisse femininity, but the painting is entitled Music. That the vibratory interrelationality of the two women has reconfigured the time-space of the canvas, and that in turn has presented an experience that is conscious time-space to the viewer, who in their appreciation, in our appreciation, enlarge that canvas, that room, that music between those two to include us. That we hear that music though no note sounds. Because we, in seeing that kind of form, participate in its reality. A painting like that, in terms of everyday traditional reality, is surreal. I'll give you an example. This is a true example from my own life. In 1973, here in Los Angeles, MGM Studios was closing down and they were auctioning everything off over in Culver City in the big airport-type hangar studios. They were auctioning everything off. And in one of these sound stages, the interior painted completely black, huge, there were about 5,000 or 6,000 paintings that were being auctioned off, paintings that were mispainted so that on camera, at different angles, they would show up. And so they were interesting, but it was all a lot of studio junk. And walking around on the floor of that soundstage with the auction going on and several thousand people crowding into the soundstage, I found a little quiet area that was like a room setting from some film with a little couch in it, a nice floral print couch, and a couple of end tables, and one painting against the wall. And I walked in, I was all alone, everything was in the background, and I walked in, and when I saw the painting, I was physically thrown onto the couch. And I sat there trembling because the painting that was in there was an original Pissarro. And the painting by Pissarro was so vibrantly real as an artistic, aesthetic, conscious space-time object that I was participated in the Pissarro painting, and the background of the auction became like a dull roar of inconsequentiality. It became a rote cardboard experience compared to the Pissarro. What we're looking at today are two scientists who brought reality to such a fine complexity that the previous states of their own science now seem absolutely passé and of only archival interest. The two figures are Mary Leakey in her wonderful book, Disclosing the Past, and Richard Feynman's QED, Quantum Electrodynamics, the strange theory of light and matter. Now, don't be frightened by QED, quantum electrodynamics. Alan Alda starred in the play just a few months ago, QED, the Performing Arts magazine at the Mark Taper Forum presentation of QED and its Feynman creator. So don't be scared of the fact that we're going to talk a bit about nuclear physics or high mathematics. What we're doing is presenting like in a Pissarro painting or in a Matisse painting. And the understanding is not to be had today. The understanding is going to be creatively distributed through the 12 lectures of science, so that it's only by the accumulation of the 12 lectures of science into a set that we will have a chance retrospectively to go back and begin to play within that set and understand what it was, not that what was there to understand, not the conclusion, but to understand that there never was a conclusion. There was, in reality, always, as a common denominator of whatever was found, the ongoing process of free inquiry. And that this set of 12 lectures of science is a morph of the 12 lecture sets that went before it, and that there were 7 such before it, so that science is the 8th set, and that these sets do not make a linearity at all, but they make a matrix, and that the matrix has a particular structure to it. It is 2 groups of 4 sets that make up the education. So that science, in its 12 lectures, as a set, goes with history, art, and vision in their 12 lecture sets also, and makes thus a kind of a quaternary, a kind of a 4-part set of sets, and that they are paired with the 4 sets from the first year: the nature, the ritual, the myth, and the symbol. And that this pair is like a pair of 4s which make an 8. Not just an 8-part education, but an 8-item or 8-element matrix that has within it a paired quaternary substructure. Something not said is invisibly hidden from normal view within this particular structure. And that is the 4s themselves are pairs of pairs. That each of the 4 groupings of the sets have pairs within them that are paired together. Science is very similar to art. Since the Renaissance, science and art were always put together. In most universities, up until recently, one would have had a department of the arts and sciences under whose aegis all of these different courses and subjects would have been taught. The arts and sciences go together. They go together in such a fundamental way that one could speak about our persons, our spirits, being at home in the cosmos. That person and cosmos have a deep resonance on level of capable of being harmonized. There is such a thing, not as man being at home in the cosmos, but of our persons being at home in the cosmos. Very, very, very realistic. And mathematically provable, by the way. We have the math now to do it. But coupled with that pair of art and science is another pair, history and vision. That history and vision together are a pair, but they're not a pair like art and science, which deal with objectivities that have their occurrence. Somewhat different from existentials, but related to them. They're objective. Whereas vision and history are processes. They are transform processes. They are media within which transforms occur. In vision, it occurs with consciousness. In history, it occurs with interconsciousnesses. Vision can be shared, but it's always a vision that someone has, some consciousness has, and then is shareable from that standpoint, whereas history is shareable all the time, and one has to do another kind of an operation, a derivative, an alchemical getting of the essence of it in order to find out for oneself what it really amounts to for you. So that history is like a group consciousness, and it turns out that the groups don't have any bounds. That history is such a deep transformative process that it can include not only all the human beings on this planet, but other life forms on this planet like dolphins and dogs and horses and mice and trees and flowers, so that history also has in its deeper reaches of understanding such a thing as what it was taught at one time as a subject, natural history, also belongs to history. And as we mature, we will find that the history of other worlds becomes an expansion of our sense of history. The life forms on the moon of Jupiter Europa are very much going to be a part of our history from about 40 years on out. The life forms on Titan, the moon of Saturn, though they have a completely different life cycle, a hydrocarbon basis which is quite different from ours. Nevertheless, they will join, and their history will join, an expansion of our sense of what history is. Out of this expanded history comes an expanded cosmos, an expanded science. Just as out of a deepened vision comes a deeper sense of person. And because that deeper sense of person so outstrips the idea of an individual, that the idea of an individual is like a kindergarten building block that has one letter on it, and that you would have to put several building blocks together to make a word. Those are old, clumsy sketches towards form compared to what the person is, and so we're very used to saying that on the level of an art form person, we're talking spiritual. We're talking spiritual not as distinct and opposed to physical, but spiritual in the sense that one is able to have that spirit immanent in the physical. We use the term embodied. So that it is possible to have an education where somebody learns to embody their vision in their rituals, in what they do, to embody their vision in their mind, into how they think. And that this is a part of the way in which the intermeshing of what was a pair of realms, one, a realm finely characterized not by nature, not by ritual, not by myth, not by symbol, but by the ecological common denominator of the way in which they function. And all four of those function in an integral way. They all integrate. Whereas the phases of our education of vision, art, history, and science all differentiate. And that the integral and the differentiable are able to be brought in a paired way, not just into an interface, and certainly not into some grand integral. The differential never integrates, but it can interface and factor in, it can embody. And so one has to be very cautious not to list differential forms with integral forms in any kind of cardinal counting way. If you do, you make a slip from reality into a condition which is known universally now as a game. One of the curious things about the most powerful mathematical and physics transform of the early 20th century was made on level of a sophisticated game form, which was so powerful that it was more real than all of the previous games, and in fact seemed to be a new kind of reality. And it took all of the 20th century to come to understand that, in fact, it was but a complex variable of a game. The thing I'm speaking of now is the development of general relativity, where time was given the expressive form of an x with a 0 superscript, and that the 3 dimensions of space would be then x1, y equals x2, and z, the 3rd dimension in space, would be x3. And that these 4 coordinates together as a matrix describe a relativistic locus in time-space with 4 dimensions. And it's true that time is a first dimension, but in the game in which that language designate was played, it was always talked about as the 4th dimension. And time as the 4th dimension should have been a clue to refined yogic practitioners at the time that something had been transposed. And what was transposed was the unconscious projection of conscious dimension into the computation without knowing that one had done this. So that actually, when it comes time for 21st century math to perform its transforms, a matrix of space-time with 4 coordinates is not sufficient to generate the reality of where our sensitivity and our spiritual penetration into complexity have already taken us. We will have to learn to redo our math with at least a 5-dimensional continuum, and probably, as string theory has already begun mooting, if you pair 5 dimensions together, you get a 10-dimensional continuum. And in that 10-dimensional continuum, in current string theory, there are 3 sets of space and only 1 dimension of time, giving the 10 dimensions. This is also, on very subtle, sophisticated way, a game. And it'll be another 10 or 15 years before it's capable of being seen through. The little tab on the kicker is that when you have 3 sets of space, 3 sets of 3 dimensions, what occurs to the geometric template is that you have cubed something. And of course, the 3 dimensions of space naturally lead to a cube. A cube has a particular quality as a structure. A cube is not only a pair of 4s, it is 3 2s. When you take a pair to the 3rd power, when you cube a pair, you also get an 8. And it is not possible for the mind to tell the difference between the 8s. Whereas consciousness can be honed in its filigree to tell the difference between the 8s. You can tell the difference between 4 squared and 2 cubed, and it makes a great deal of difference. The problem goes back to the I Ching 5,000 years ago. To pair yin and yang, to get to the 8 trigrams, you have to introduce a 3rd line. And the only way to do that is that you have to repeat one of the 2 lines, so that you introduce a 3rd, which is a repetition of one of the other original pairs. And this will give you the 8 trigrams, but it is not on the basis of 2 cubed or 4 squared, but on the basis of a manipulation. It took a long time between Fuxi, who first discovered the trigrams, and the Duke of Zhou and King Wen, who refashioned the trigrams into the 64 hexagrams of the I Ching and made it a discursive, transform language. It took approximately 2,000 years for that to happen in China. It happened a long time ago, but it's an object lesson for us. It was only after the 1920s in the 20th century that a couple of mathematicians and nuclear physicists understood the importance of this, and the most famous of them was a man named Niels Bohr. And when he understood, through his own struggle to understand form and the way in which conscious dimensioning of time-space underwent a paradoxical re-emergence in a realm that could only be called surreal traditionally, and yet it was completely normal in terms of an expanded cosmos. And so Niels Bohr was one of the first individuals in the West to take the old Chinese Taoist symbol, the yin-yang symbol, and put it on his family crest. A Danish man putting the Tao symbol on his family crest, because he had come to understand that unlike thousands of years of Chinese scholars who had thought of this as being transcendentally mystical and having to do with all kinds of things like diet and elixirs and immortality, Niels Bohr was one of the first to understand, as Lao Tzu had some 2,500 years ago, that you're dealing here with reality, with the way in which reality can not only be understood and appreciated, but expressed in a way that registers in a smaller subset of reality, so that there is such a thing as a practical, smaller unit of the infinite cosmos also being capable of being understood realistically, even though one characterizes it with a limited, quantifiable, numerical weight of value. This is to say, it is possible to quantize a limited time-space and not fall into an illusion of misrepresentation and a delusion of mischaracterization. But you have to do it consciously so that when you do your real appreciation, you're able to take that realistic appreciation and put it through a process temporarily of quantizing it and then bringing it back out and expressing it in such a way that you can deal with a limited time space but with a definite, finite numericality to it. The process of this is known in contemporary physics and mathematics as renormalization. And it's very strange at first, but one can get used to the fact that it's like making a translation, only the translation is not into a foreign language. The translation is into understanding that a limited case of an infinite cosmos can have a finite quantization that works reasonably well, and yet one is aware that it's not the whole truth. And so realistically and honestly, one says that this is the most probable case. There's a beautiful presentation of this in a science fiction film of about 50 years ago, The Day the Earth Stood Still. And the alien Klaatu is talking to the screen presentation of Albert Einstein, who has his board filled with the equations, played by Sam Jaffe. And Klaatu says to Sam Jaffe, Einstein, he says, "This is the right answer here." And Einstein looks at the blackboard, he says, but this is obviously not the whole thing. It must be an error. And Klaatu says, well, it's not the whole thing, but it's good enough to get me from star system to star system. You can do interstellar navigation with this refinement, as long as you understand that the displacement from the real has already been recognized and you factored it in as a play of the expansion possibilities, and that the expansion possibilities are not just for a little bit further, but for an infinity that's further. So that you deal with the finite space-time universe with a conscious dimension that this is the probability, this is the possibility currently that we can use, but it is only on the basis of a loaned tool, so that one finally comes to a great, catastrophically, no, let's use the Tolkien word, eucatastrophically realization that no one owns the cosmos because it is not ownable. It ain't real estate. You can't own the moon. You can't own the earth. You can't even own one photon or one atom. There's no way to get a title deed that's airtight legally to that. So that the only reality that's there is that we're living on a gift of circumstance temporarily and only shareably, and that this is the actual state of the cosmos, of the universe, of the real. And in the 21st century, as this comes through in an education, obviously something similar to this, the realization will be that all of the derived political forms of the past are extraneous. It isn't that this is right and that's wrong, or all of these we can work with and these we can't. All of them are extraneous. They were made on the basis of an integration using existentials in a game way and have no relationship to reality. As Jack Kerouac wrote in one of his poems one time, he said, "It was Friday afternoon in the universe." Where is it Friday afternoon in the universe? Probably in the Jewish communities of any city on the planet. But one can see, what time is it? Is it Pacific Daylight Time on Altair 4? It's not only irrelevant, but it's extraneous. And as we begin to expand ourselves out of the sandbox of our planet, we're appreciating the fact that even on large level of clusters of galaxies, we can work with specificity, but always just conscious that we're being given tools and gifts to work with in a shareable way temporarily. There are about 30 bodies in the local cluster of galaxies. 2 big galaxies, our own Milky Way and Andromeda, and about 27 or 8 smaller bodies. And this whole cluster of galactic structures actually constitute a matrix that has the same dynamic moving through a very larger subsection of the universe. And that this whole cluster of galaxies, galactic structures that we're in, is moving very definitely, very fast. You would be very glad not to have any kind of stable coordinates in reality. All of us would have lost our gravitational integrity long ago. We're rushing towards the Virgo cluster of galaxies, which contains about 1 million galactic structures. And its gravity is so much more than ours, pulling us toward it. And in many, many billions of years, our galactic cluster will join the Virgo cluster. It's on this level that this kind of education is the only realistic approach that we're not learning to get answers, as Feynman said. He said, I don't care about the answers. I'm learning to learn. I want to have the process of inquiry going on because I enjoy it. I like it. It's something for me that I'm able to participate in. We're going to take a little break and we'll come back and look at some more. If I say I live in the Bay Area, you can't know what I'm talking about. If I articulate and say I live in the Bay Area, you can hear it. The source of the Bodhisattva's compassion is that ignorance is inarticulate. It's not so much that it's wrong as like in an error, but it's inarticulate, so it can't be appreciated. And because it can't be appreciated, there's no possibility of being understood. So this is an education that is not trying to deliver correctness in terms of a subject, but to present the possibilities of appreciation in terms of a flow. And that flow, as it continues, has the ability to gain complexity and have density and be capable of penetration from many different angles at once without ever being concerned whether it is right. Wisdom is not concerned with being right. In a colloquial way, one says, we're learning to generate a multidimensional consciousness so that we're not uptight whether or not we understand this particular line of instruction. Almost all education is based on this tense geometricity, and you're going to be tested on it. And the catastrophic nightmare for most human beings of their educational background comes from this inarticulateness of the so-called educators. It's not so much that they're wrong, they're not even in the game. And the game is not even in reality. So that there are many orders removed from being able to teach. When someone learns the difference between existentially being and having your faculties stuffed within your certainty, and the sudden release of liberation, where the field of capacities can just flow through you and out into everything, and the realization that that liberation brings, that you are not a limited form at all, but that you are vast floral fields of possibility that temporarily juxtapose and come within this body or this mind and go off, and that one has not only thousands of lifetimes, but infinite life. The desperateness of error patiently gives way to the compassion of deep wisdom. And so this is an education presenting this, and again presenting this in such a way that you could recognize any wisdom tradition on the planet, or even on other planets, through appreciating this. So when I get into the material, it's not that it needs to be understood. It's not that the mathematics and the physics are so difficult, and if only I could remember. You don't have to. Just open up the largesse of appreciation, and I'll teach with that. One of the most interesting aspects of 20th century science was the peculiarity of the individuals involved. We'll get eventually to appreciate Mary Leakey and Richard Feynman. One of the curious things about Mary Leakey is that when she was a young girl, her parents took her on some sketching trips. She was an English girl and she happened to enjoy sketching. And one of the sketching trips they took her on was to France. And her father made a contact with someone who knew this French man, the Abbé Bruel, and he was the first to publish art books on Paleolithic art in France, 1901. And Mary Leakey, as a young girl, got to go down into the French Paleolithic art caves, and she began realizing, as she was sketching those Paleolithic works, that she felt more at home with those Paleolithic art forms than she did in her own life. That they were not strange to her. Her own life was really strange to her. These works were beautiful to her because they revealed to her that she was not limited to being a little English schoolgirl, that she had some kind of deep ancient affinities with something mysterious. And towards the end of Mary Leakey's life, she published a book on Paleolithic art in Africa, Africa's Vanishing Art, the Rock Paintings of Tanzania. And she loved making the sketches herself. This quality of Mary Leakey to let herself go into the very ancient aesthetic of Paleolithic artists was like a template. It was like a hand size that she later on could hold up to looking at the geologic strata of Old Duvai Gorge and learning to see that man has lived for millions of years. When she was a girl, the best estimate of man's age was about 6,000 years. Adam had been created in 4004 BC on August 21st at 4 in the afternoon because an Irish cleric, the Bishop Usher, had figured it out by computing it through the Bible. It was considered an anomaly that someone like Thomas Jefferson considered that life was millions of years old because he had personally financed an expedition to exhume the skeleton of a mastodon off the American Atlantic coast, and was quite convinced that there hadn't been mastodons in North America for very much longer time than just a few thousand or even 6,000 years. It wasn't, though, until the man who married Mary Leakey, Louis Leakey, came out with a book called Adam's Ancestors, the evolution of man and his culture, that it suddenly became possible on a worldwide level to entertain the possibility that man was not only ancient, but primordial. That man was so old that his earliest traces were in geologic strata of the earth. That we were not recent arrivals by some miracle of sudden appearance, but that we had emerged with great articulate patience over hundreds of millions of years. And that man was therefore grand in a scale that was unheard of and unheralded. And when Louis Leakey met Mary Leakey, he fell in love with the woman who could see beyond the hand scale into that Paleolithic scale. And she was able to appreciate in him that he was not a, quote, white man. He was not an Englishman, but he was a primordial man. In fact, when he was young, Louis Leakey was raised. His father was in the missionary cycle of service in East Africa. He was raised with Kikuyu tribes boys, and he was raised to be a tribal Kikuyu. And he didn't realize until he was sent away to England to go and study that when he dreamed, he didn't dream in English, he dreamed in Kikuyu. And he wrote 2 biography portions. One is called The White Kikuyu, the other is called White African. And Louis Leakey was always an elder of the Kikuyu tribe. And when they had in Kenya trouble with the Mau Maus in the 1950s, it was Louis Leakey who went personally to Jomo Kenyatta and presented himself as a tribal elder of his own tribe and made that kind of contact. And it was Kenyatta who got a very clear, articulate humanity from Louis Leakey. Louis stood and took him to the door of the hut and pointed out into the distant landscape to Mount Kenyatta. He said, "You are named for that mountain is not named for you. We all belong to the land, and we all will find an articulate way to be here together, not through death and terror, but through life and nature, that we are all related. I am a Kikuyu. I'm not an Englishman." And he explained all this in Kikuyu language to him. It was this quality of Louis and Mary Leakey together brought into a pairedness that made them have the tenacity to look for something no one had ever seen, no one had ever suspected before, no one believed that it could be found because it didn't exist. And for about 25 to 30 years, Louis and Mary Leakey, without any funding, more than just a few handouts here and there, persevered and persevered, and it was only late in their life that they found the first evidence of man living millions of years ago in a form different from the species that he has and yet recognizably related to it. And the first evidence came from taking a ferry boat ride on Lake Victoria and passing an island called Rusinga Island, and from the deck of the ship, Louis Leakey, deep in a Kikuyu African nature trance, saw that the evidence was there. And he wrote a little book called By the Evidence later on, an autobiographical. He had this ability to open himself up and to be able to envision something that could not be seen but the eyes, but which a conscious time-space spiritual seeing made possible because the cosmos resonated to him. Later on, his son, one of his sons with Mary, their son Richard, was flying in an airplane over the wastes of northern East Africa, over an area called Lake Turkana, and he, from the airplane, saw the same way, saw that this little peninsula of barren, volcanic soil that jutted out into Lake Turkana was the place for more evidence. And it was later on there that they found the skeleton, the complete skeleton of a young hunter man who lived 2 million years ago. And that this skeleton, the Nariocomio skeleton, I'll bring the Harvard monograph on it, a great big $200 book. They found that the skeletal articulation of this young man, he was about 17, he was over 6 feet tall, and he was able to run probably as fast as any Olympic runner, and had the bone stamina. He could have run top speed all day. And that early man was unbelievably gorgeous in terms of stamina. That he was not a marginal scavenger begging his way through, but that primordial man was beautiful in his articulate ability to synthesize the dynamics of life, and won through beyond species limitations to us, carrying that DNA, which has modified itself less than 1% since then, so that we inherit an incredible dramatic story whose articulation is only in the last 25 or 30 years become able to be said. And we'll look at that. The hero of it is not Louis Leakey, but Mary Leakey. She's the one who, over a long lifetime, went out seemingly alone because she learned from Louis to take her Paleolithic art vision and expand it to the geologic vision of his Kikuyu Africanness. And she learned to do this. And she went out not with anyone else, but she went out with a pack of Dalmatian dogs. Sally was the head female of the dog pack. And she and Sally and the rest of the Dalmatians and her little cigars that she smoked and her little sun hat that she had, and she spent the better part of half a century out there. She was the one that brought the material back to camp. She's the one that dug out the millions of years of heritage of man originally. And it was the patient sifting of Louis in the camp with her to see how all this came together. And through many spurs that didn't develop, they finally laid an appreciation field, not the right way, but the right appreciation field, out of which has emerged our understanding now of the origins of man. Very similar thing with Richard Feynman. Richard Feynman, born in the kind of Brooklyn, New York, urban, fast way of getting things done, and yet respect for the complexity of circumstance. Richard Feynman, all of his life, was uncomfortable with honors. He was uncomfortable. He said he was singled out in high school to be a part of an intellectual club. I think it was called something like the Aristocrats. And he said all of the time was spent in this club discussing who they were going to let in. Who else would be our peer? And that was what it was about. And he said the same thing is true about a lot of science organizations of distinction, the National Academy of Scientists. He said, I resign. He said, I'm sorry I got the Nobel Prize, but it would have caused more of a stir if I had refused it. He said, honors scare me because it conditions us to look for achievement as the hallmark of our activity, and that always is a game, a losing game, because it deadens our ability to appreciate the ongoingness of inquiry, which alone is of interest. Feynman was famous towards the end of his life on the board investigating the Challenger tragedy, where one of the space shuttles blew up in 1986, killing all aboard in front of a whole world of young children who were looking at one of the female astronauts as an example of the beauty of safe space. And Feynman is the one who concentrated and brought the situation to its dramatic fulcrum. He took one of the rubber O-rings as part of the rocketry design and dropped it into a glass of ice water and showed that the cold immediately changed the molecular structure from rubber to something that was fragile and could crack and nick. And those microscopic nicks are not visible with the eye, but that they receive tension from their operation, and it cracks and granulates their structure so that the seals broke and the rocket blew itself up because of this. Feynman had the ability, like Mary Leakey, like Louis Leakey, to go into a field of inquiry completely open so that their consciousness was scaled to the cosmos. Their person was scaled to the cosmos as a whole, so that what they saw through a calibration with the real, and were able to renormalize, to transform that, to bring that scale of zero Tao wholeness, mysteriousness, into an interface on a more limited scale where there was a finite measurability of something. And so to understand that at this scale, this can be measured and is as good as we need. When we look at Cambridge University Press book, Early Quantum Electrodynamics, the paperback has the photo on the cover, we see four figures that are the generation just before Feynman. We see Niels Bohr, we see Paul Dirac, we see Werner Heisenberg, and we see the beautiful figure here of Wolfgang Pauli. Four figures, this is Pauli, this is Dirac. Four figures who together form like the meat of a lineage. And I want to just give you that lineage, not so that you have to remember it, but just so that you heard it once. Not to hear it as information in a line, but as, again, a phase form morphing, a brief presentation, so that you can gain the beginnings of an appreciation that there is an ecology. There is a cycle of discovery whose inquiry had both a synthesizing thread, finally called a path integral, quite clear, but at the very same time had a differential conscious dimension of infinity. And that this didn't bother anyone, that infinities were wild and loose outside of the confidence in the limited finite measurability, because they had the two together in a complementary fashion. Most of the focus of the dramatic crunch of the story happened at one place. Cambridge in England happened at one building, the Cavendish Laboratory, and happened because the Cavendish had been set up in a very interesting way. The original powerful chair for the Cavendish Library was a man named J.J. Thomson. And J.J. Thomson was a physicist in the 19th century and on into the 20th century. But he's famous for being the first human being on our planet in our history to ever understand that there was something other than an atom, that the atom had at least a working part called an electron. And he did this in 1896. And in 1896, the discovery of the electron was a great puzzlement. And in 1996, Cambridge, in order to honor their wonderful contribution, published Electron, a centenary volume. And it came out, and it is a centenary on the 100 years of the discovery of the electron. Now, Thomson's original understanding was that an atom must be a thing. It goes back to an old tradition, which in physics of the late 19th century was actually called corpuscular theory. Corpuscular, body. It has to be a thing. It has to be a body, an existential, something. And as late as 1913, Thomson was still writing books with the title The Corpuscular Theory of Electrons. And I'll bring in a copy next week. But by 1923, when he went to Philadelphia, when he gave a series of 5 lectures at the Franklin Institute, The Electron in Chemistry, there was a complete change of understanding that the electron, in fact, has a different quality from anything that we have known. And this is how the preface reads from J.J. Thomson, written at Trinity Lodge in Cambridge, June 1923. It has been customary to divide the study of the properties of matter into 2 sciences, physics and chemistry. In the past, the distinction was a real one, owing to our ignorance of the atom, the structures of the atom, and the molecule. The region inside the atom or molecule was an unknown territory in the older physics, which had no explanation to offer as to why the properties of an atom of one element differed from those of another element. As chemistry is concerned mainly with these differences, there was a very real division between the 2 sciences. And in older universities all over the world, they were in separate buildings. They are still being built as separate buildings in academic institutions all over the world. 80 years ago. In the course of the last quarter of a century, however, the physicists have penetrated into this territory and have arrived at conceptions of the atom and molecule which indicate the way in which one kind of atom differs from another and how one atom unites with others to form molecules. These are just the problems which are dealt with by the chemist, and thus, if a modern conception of the atom is correct, the barrier which separated physics from chemistry has been removed. While this was going on and happening, there were 2 men that had almost the same name involved with the early Cavendish. One's name was William Henry Bragg. The other's name, his son, was William Lawrence Bragg. And William Lawrence Bragg would be the head of the Cavendish when Watson and Crick would discover the structure of DNA, so that atomic and molecular structure is related to the structure of the double helix of DNA at the same place through the same flow of a field of inquiry, of a differential consciousness tuned to the cosmos and not tuned to any preconception, however ingenious, however so-called universal. It's interesting because the father, William Henry Bragg, had done some work, had taught in Adelaide, Australia, had come back to England. Their family was originally from the upper part of England, from East Cumberland, which if you look at the travel guides, the Shell Travel Guide of England, it says there's a dearth of great houses in this part of England. They're just like stone cottages. That the land up there belongs to the people who work it, to yeoman farmers. That's what it belongs to. And the Braggs came out of that kind of a background. They were used to working with their hands to earn their daily bread. And this quality carried over, and William Henry Bragg, when he came back to England, he was put at Leeds University in a very industrial and kind of a grim part of England, and so it was with great joy that he was corresponding with his son about the latest developments in 1912, that there was something going on. And here is a letter from the son to the father. The Jeans in here is James Jeans, a famous scientist of the day. Dear Dad, I'm so glad you like the notes on genes. I'll bring the notebook home and we can go over it. He's been doing the pressure of radiation business lately, and according to him, it is the most utter rot. Now he's talking about 1912, about investigations into radiation, and that brings up the figure of Ernst Rutherford. Rutherford, also a very ordinary kind of a man. He was born in New Zealand. He was born in one of these farming communities, agricultural communities in New Zealand, and he was discovered to have the right patient articulate temperament for not only investigating, but by building his own equipment. And Rutherford was one of those men who could envision an experiment and then build whatever equipment he needed to simply carry it out. And he spent a lot of his time up in Canada at McGill in Montreal, and eventually worked his way to where Rutherford became the figure who was central in the development of physics in England. He was called by everybody who studied under him Papa. Like Papa Hemingway, only Rutherford was a real Papa. Rutherford loved his boys to get on with their work and learn to talk with each other without prejudice or preconception, and that whatever preconceptions were there were always hypothetical, and that the two parts, the experiment and the vision, both went together and formed an overlay which was the possibility field. And Rutherford taught this way. He also delivered a course at the Franklin Institute. He was the inheritor, after J.J. Thomson, of the Cavendish laboratory. This was delivered the next year from J.J. Thomson's on the electron. This is September 1924 in Philadelphia at the Franklin Institute, The Natural and Artificial Disintegration of the Elements. Because he was dealing with radiation. In fact, his first book on radiation published by Cambridge was 1904. And the very next year, in 1905, he had to put out a second edition because it was totally revised, because in the matter of about 6 months, he found that everything that he knew last year had already been changed to such an extent he had to write a completely new volume. And when he brought out the third edition on radiation in 1933, it was about twice as big and 50 times as dense and compact, full of incredible events, because by 1933 the Cavendish laboratory at Cambridge was full bore into a monumental realization that was spearheaded by a man named Dirac. And he's usually known by his initials, P.A.M., Paul A.M. Dirac. His early collected works are published in one of these great tomes by Cambridge. Cost about $400. Dirac is the first man to write a comprehensive textbook, and it was published by Oxford in 1930, called The Principles of Quantum Mechanics. And by the time the third edition of this came out, quantum mechanics had become the understanding of physics throughout the world, and he lived long enough to put enough notes to make a fourth edition, which is the one currently in print. still read. Still read. Dirac, like Feynman, was someone who always eschewed honors. He didn't want to be singled out. He just wanted to work. And so he's largely unknown. But the fact is that Dirac is an extraordinary figure, and one of the most extraordinary things, towards the end of his life, he died in 1984. They retired him from Cambridge. He was getting old. You have to retire. And he got an invitation to keep on teaching in America at Florida State University. So he went to Florida State, and when he saw the American students at Florida State, he realized that they didn't know anything about science, that they were learning science in such a completely unreal way that he set down in less than 70 pages the principles of general relativity and wrote it out in a series of 35 sections so that you could, in a little few minutes sitting, get each section, and that you could navigate your way through and come to understand something that was extremely important. He says in the preface, this is Dirac in Tallahassee, Florida, February 1975. He doesn't say it, but it could be friends. Einstein's general theory of relativity requires a curved space for the description of the physical world. A curved space. Immediately, our appreciation glows because he's saying the geometricity of lines and planes and squares and rectangles are extraneous to understanding the real. Space is not a vacuum that contains lines and planes and cubes, but that space itself is modulated with time, and that time-space curves all the time. Einstein's general theory of relativity requires a curved space for the description of the physical world. If one wishes to go beyond a superficial discussion of the physical relations, one needs to set up precise equations for handling curved space. There is a well-established but rather complicated mathematical technique that does this. You can learn it if you would like. And I can teach it, he's saying, if you like. It has to be mastered by any student who wishes to understand Einstein's theory. This book is built up from a course of lectures at Florida State. Its aim of presenting the indispensable material in a direct and concise form. It does not require previous knowledge beyond the basic ideas of special relativity. You see my little friend the fly here? It will enable the students to pass through the main obstacles of understanding, not to confront them and conquer them, but to pass through as radiation passes through. And this brings us to an appreciation. Radiation. Radiation. That matter radiates. The first element to be looked at was looked at by a woman, Marie Curie, radium, that it radiated, that it gave off rays. It gave out energy in waves that was mysterious, and she wanted to know. And so deep was her love of the inquiry of it that her daughter became an equally famous physicist to her, and that her daughter and her daughter's husband together were some of the most forceful physicists in the 1920s to bring about the revolution that happened in the early 1930s at Cambridge, at the Cavendish lab, out of which someone like Richard Feynman is like the boy genius inheritor of that whole differential conscious inquiry mode. Because when Feynman came into play, he was a cause célèbre as a boy math genius. He was still a teenager when he was chosen by Robert Oppenheimer to be one of the top mathematicians of the atom bomb project, the Manhattan Project at Los Alamos. Because there was something about Feynman, like Marie Curie, like Ernst Rutherford. He understood that we're not after solutions. We're generating an expanded inquiry that expands in such a way that it allows for a more expanded inquiry to occur, and that this is a development which nature respects and will sing to us the songs we need to hear. If we hum the music, nature will give us the words. Or if we hum the words, nature will give us the music, because the two of us together make what's real. And it was Feynman who finally, like Rutherford, made his own tools to express, and they're called Feynman diagrams. And they're the world standard now for being able to talk about this. Because most of the math got so expanded and so articulate surrealistically that it takes almost a lifetime to learn to get to that sophistication, whereas the Feynman diagrams do something which is radical. It's very similar to the way in which Enrico Fermi found a solution to some of the problems that were bugging physicists in the early days. And this is how it reads. This is a Princeton University Press, QED and the Men Who Made It. And on page 75, just a little quotation here. The author is talking about the birth of quantum field theory. He's talking about Heisenberg and Dirac and the Pauli and the difficulty of the mathematics. And finally he says, and he's talking here, he'll mention a Hamiltonian. It's a different conception of space, a matrix conception of space, rather than by points. Once again, in the math, the Hamiltonian from which the equations of motion follow was written down. Fermi then showed how to eliminate the scalar and longitudinal oscillators, which were making the computations enormously complex, and derived an effective Hamiltonian that involved only transverse oscillations, but in addition contained an interaction term between the charged particles. This is why the big center in Illinois in the United States is called the Fermi Center. Like Feynman, he showed the way to go a transverse diagonal rather than sticking with the geometry of the squares and rectangles of the complex ideas, and that if you do so, it is not just a shortcut, but that is like exposing the facet of a jeweled form of vision, so that you cut the whole field of inquiry in a new way. That Enrico Fermi and Richard Feynman were like ancient diamond cutter bodhisattvas that showed how to recut the mind so that it thought in a different way. Not to use geometric form models in the first place. We'll continue next week and we'll take our time and develop all of it.